Now that we've just done vector addition, we're going to do vector subtraction. So let's get going with that. And a logical way to think about vector subtraction is just simply adding the opposite. Namely, if you have vector A minus vector B, you have A, and you add to A the negative of B. Looks like a simple math operation, and it is. But there's another way I want to show you. I am going to model for you right now that I think is a little nicer visually, and sometimes if you're doing graphical vector analysis, it just lends itself to a nicer, cleaner analysis. A little hard to explain that, but you'll probably see that along the way. So here it is. It's the tail-to-tail method, and we're going to do A minus B by subtracting these two vectors, A and B. So first, you measure and move the tail of B to tail of A. So I'm going to take B and move it to the tail of A. But you can't do that till you measure B, so there's its length. You've done that carefully. And now you know that you're parallel to B. Well, you have a nice starting point to draw it with your instrument, and you draw it in. So there I've moved it to the tail. I've moved the tail of B to the tail of A. Now they're connected tail to tail. So you're going to draw from tip of B to the tip of A. So that's how you're going to do it. When you have A minus B, you go, with the tips, you go from the latter to the former. So B to A, that's the direction you're going to go. So bring in your straight edge, and you draw the resultant, and you've measured it. You can measure it with an angle and all that. But that is representing vector A minus vector B. So let's check this by doing it maybe the more intuitive way by adding the opposite, A plus negative B. So we'll do regular vector addition. Here's A, here's B. Let's add negative B to A. So we're going to do vector addition. And what do you think the negative of B is going to be? I'll bet your intuition is going to be correct. Namely, you put the arrow on the other side, and that would be negative B. So we have to know the length of B, which we already do, and I see how I've got it parallel to one of these parallel lines. Well, I connect up over here, but I'm going to add the negative to the tip, which means I'm going to have to go up this way. It's going in this direction. So there it is. Parallel, arrow on the opposite side, and then you connect the unconnected tail to the unconnected tip of the last, and you will have your answer. Now, there it is. Does it look like this result is the same as this? And I'm sure you will say yes. So A plus negative B gives you the same result for using either method. And as I said, I prefer this one, but if you really get confused, you can always revert back to this. We are now going to do another vector subtraction problem having to do with motion, two different velocities. And probably as we go through this, you'll see how the tail-to-tail method of vector subtraction kind of makes sense. You may or may not see that, but I'm suggesting it does. Well, a car is traveling at 50 kilometers per hour due east, going around a corner, slows down to 40 kilometers per hour, so it's slowed down and it's in a new direction. What's the change in velocity? So we'll get magnitude and direction, of course, because velocity is that. And a change is final minus initial. So there it is. That's the equation for the change. And then we'll check by adding the opposite, which is the delta V is V plus the negative. So we've already gone through that. Let's do it. 1 centimeter is 5 kilometers per hour. Should fit well on your paper. Keeping in mind delta V is V minus V0. So we'll connect the tails together of these two vectors. And then the tips go from V0 to V. That's how we connect the tips for the actual quantity, delta V, which in this case, that's our resultant, is delta V. So we're going to begin here at this dot. And we bring in our 6 and 1 and draw a 50 kilometer per hour due east. Let's see, that's going to be 10 centimeters. So it goes all the way out to there. There it is. Label it. 50 kilometers per hour east. And now, later, since we're gonna put the v, which comes later, 40 kilometers per hour, 40 degrees north of east. So let's go 40 degrees north of east. So that's about right there. And put it to the right length. Looks like that's going to be 8 centimeters in my scale here. So there it is. The vectors are specified. They're connected tail to tail. And when we connect the tips like this, we actually have the change. Now it kind of makes sense. So there it is. It's 6.5 centimeters. But let me express why it makes sense, because here's our initial. This is how we are initially moving, this direction and this magnitude. And then it changes by this much, upward and to the left, to give you a resultant of this. So this maybe looks like the resultant, but it's the addition of this vector and this vector, really, to give us the final. In other words, the initial plus the change equals the final. Intuitively, that probably makes really good sense to you. Does to me anyway. I'm trying to help you here. Now, I'm going to unscale the 6.5 centimeter resultant here. 5 kilometers per hour per centimeter gives us 32.5 kilometers per hour. So there's that's the size of that change in velocity. It's interesting. Now, measure the angle, and that angle turns out to be right around 53 degrees. Let's specify here, 53 degrees north of west. It's really part of the answer for the delta V. Fully specified. Now let's add the opposite. So we're going to parallel move, as I've already shown you how to do, this one over to here, adding to the tip of well, in this case, V plus V0. That's what that is. Plus negative V0, actually, right? So it doesn't matter what order we put them in. I connected them tail to tip. And the resultant of those, just like this. You can visually see that it's the same as what we did at first. So V plus negative V0 is delta V. Same thing. Again, my preference is what we have over here. Now, some interesting observations. I would like to ask you, what's the change in speed? Thinking. The change in speed, let's see, it went from 50 to 40 kilometers per hour. What is that change? It's 10 kilometers per hour. Okay, you're not surprised about anything yet. Now, what's the magnitude of the change in velocity? Thinking again, well, let's see, the change in, oh, we did this. And the size of that change was 32 kilometers per hour. I'm just rounding it down in this case. Well, does the magnitude of the change in velocity equal the change in speed? Looks like no. Does that make sense to you? Well, think about it. Speed is the magnitude of velocity. I just made a statement. I wasn't tricking you. Speed is the magnitude of velocity. By definition. Okay, I don't see 10 and 32 being the same. The speed changed by this much, the magnitude of the velocity, of the velocity changed by that much. Those are not the same numbers. Doesn't it sound like they should be? Well, if you're thinking about this dilemma, you may have come to realize already that, well, wait a minute, something else is changing. This is a vector. A vector has magnitude and direction, and the direction has changed as well. So now does it make sense to you? Of course. What? Well, maybe. And here's the thing. This magnitude of the change in velocity is not how much the speed changed. The speed changed from 50 to 40, but because we have a directional change, the velocity changed even more. And this is real. It actually changed by 32.5 kilometers per hour. If I had a greater change in direction from east to even say up here, the blue vector was up here, then that delta would be starting here and it would connect way up here. Can you see that that's a longer delta v than the one we had? Which means, because change in velocity corresponds to acceleration, there'd actually be more acceleration involved. And all that is borne out in practical reality when we have these kind of motional changes take place. So the fact that we also have a change in direction means the change in velocity was more. If we put this blue vector in the same direction as this and it stopped right here, then this would be 10. But because the direction has changed, now the change in velocity is actually a lot more. But it'd be really hard for you to answer the question. Looking at this original problem, from 50 kilometers per hour to 40 kilometers per hour, from east to 40 degrees north of east, you say, well, how much did the velocity change? You would be tempted to say 10. And you couldn't figure it out in your head from looking at the numbers what it would be. But by our vector analysis, initial and final, and see what the change is, we can quantify exactly what it is. So that just increased your understanding of the nature of vectors.